Okay, so welcome to the course. So today I want to talk a little bit more about how we specify systems, services. So I want to talk a little bit about this piece, the model, failures, and synchrony. So what kind of failures we assume, also whether it's asynchronous or synchronous or partially synchronous. So this changes a lot the algorithm. We saw that sometimes it's impossible if the model changes a little bit. So I want to talk about this, and then we'll start talking about failures more. But let me first talk a little bit about what kinds of failures, what kind of synchrony. So let's move on from this. So failure assumptions for nodes. So I'll talk a little bit about different kinds of failures. So we talked a little bit already about failures. So we want to talk about the model. So the algorithm runs on some kind of system. And so failure and timing or synchrony is very important. What do we assume? What kind of failures do we support, for example? So let me talk about 4 kinds of failures that people normally talk about. So crash stop, omission, crash recovery, and Byzantine or arbitrary. So if a node that doesn't fail, it's called correct. So when we make an algorithm, there's always going to be a certain number of nodes that don't fail, and then other nodes that might fail. Okay. So these are the kinds of failures. So the first one, the simplest one, is called crash stop. This is this kind of obvious one. When the system crashes, it just stops. Doesn't send anymore, doesn't receive, just goes dead. Okay? So by default, in many of the algorithms, in real systems, this is very common. This is a very common kind of failure where the system just crashes. So this is the failure model we're going to be taking as a default. But I want to still ask you a question about this. So this seems very simple, right? Node just crashes. So they crash and they don't recover. So a node crashes and it disappears from the system. But in real life, I want to discuss a little bit. What happens if I crash, my computer crashes and it reboots? Okay? So how do we model that in this kind of a setting? Let's say there's different ways to do it. Let's say this computer just crashes. And so it's part of some algorithm, and maybe I reboot it 5 minutes later. So how do we model that? Because it starts working again, right? So in this crash stop model, there's actually 2 ways to model such a machine, such a computer. What happens if I reboot? In this model, when it comes back, how does it come back? Let's say I reboot it. In a crash stop model, how does that look like? Well, it's actually like a new node. Strictly speaking, if the node comes back and joins the system again, it's like a new node. It's not the same one anymore if we use crash stop. Okay? Another way of looking at that is if the node crashes and reboots, then it is the same node, only it was dead for a while, but actually it comes back. So that's recovery. But that's actually a different kind of coming back. That's called omission. So crash stop is the simplest. Omission is actually a little bit harder failure model, more sophisticated, more subtle. Because the node just is working, right? And just forgets to send or receive messages. Maybe some messages doesn't send them. Okay? So the out buff just is empty. You make it empty. It's like the message disappears. Or the in-buff disappears. Message just disappears. So it's called send omission and receive omission. So that's another kind of error that happens sometimes, where the messages just disappear. Okay? So this is called omission failure. Okay? And so if a machine crashes and then comes back, maybe it's like that. Okay? Who knows? And then there's a third kind of failure, even stronger. This is called crash recovery. So this one is when the node really is allowed to recover. That means it's allowed to reboot and come back. And this is called recovery. So it's a special thing. Okay? So this is not like crash stop. In crash stop, when the node comes back, it's a new node, because a node, when it crashes, it disappears forever. But in crash recovery, you let the node come back. And when it comes back, it gets a special event called recovery that lets it do some kind of fixing up stuff. Restarts a recovery state. So this typically is the kind of thing that happens with databases and disks. Because a disk is a stable storage. When the node crashes, the disk survives. It's still there. And when the node comes back, the disk is there. So this stable storage actually survives the crashes. Okay? So this crash recovery is modeling what happens with disks and with databases. So some of the memory disappears, and some of the memory is stable and does not disappear. Okay? So crash recovery is a little bit subtle. It's not quite the same as crash stop. Crash stop is very easy. Node crashes, boom, it's over. Here, what happens when the node recovers? Well, different things can happen. Maybe the node crashes and never recovers. That's possible. Or maybe it crashes and recovers, and a little bit later it crashes again and recovers again, crashes, recovers. So it's always crashing and recovering. This actually is very bad. It's almost as bad as real crash forever. So this kind of a node is not considered to be a very good node. It's called unstable node. So this in a disk, then you don't really know what you can do. So this is kind of unstable. So a node that is unstable is also considered a faulty node. So a correct node will only crash and recover a finite number of times. After that, it just keeps working. So during the algorithm, maybe it only crashes and recovers once or twice, and that's it, and it's okay. So this is like a very practical fault node. So a correct node will eventually, which means after a finite time, it does no more crashes, and the algorithm can run. So it only recovers a few times. And if it's always recovering, then actually the algorithm maybe never terminates. It can actually keep the algorithm from terminating if it's unstable. If it does not let the algorithm make enough progress each time, then this is not good. So unstable nodes are actually very bad. So a correct node is only going to recover a finite number of times. So that's what disks usually. Nodes with disk, with stable storage, are going to be like this. Okay. So we invent this because disks are like this. This crash recovery. And the final one, which we already mentioned in the first lecture, is called Byzantine failures, arbitrary. So here the node actually is running different code. Maybe it didn't crash. It can send messages, different messages. It can have different state. It can run totally different code. It can also behave maliciously, which means it's trying to break the system. So it can be very nasty. And nodes can collude. That's when several malicious nodes are actually working together to try to break the system. So it's really a worst case. Byzantine, it's where the nodes are intentionally trying to break the system. The other failure modes are more like random events. Crash stop is like random, omission is random, crash recovery is like random. But here it's not really random. Here it's intentional. The nodes are trying to break the system. In crash recovery, usually it's not like that. It's just a random crash. But Byzantine is really worst case. And you assume the nodes are trying to break the system. Okay? So we have these 4 different types of failures that we're going to talk about. Crash stop failures, omission failures, crash recovery, and Byzantine. These are 4 very common kinds of failures that we can assume. And there's more failures, weird ones, but these are actually the most important ones. There's actually a hierarchy between these. So some of these are special cases of other ones. So what do you think? So that means, for example, Byzantine, it's pretty clear that all of these other ones are special case of Byzantine. Huh? Byzantine can do anything. So crash recovery is kind of Byzantine. Omission is kind of Byzantine. They're all special cases. But there's other kind of hierarchy in here. Some of these are special cases of other ones. So what do you think? We're going to explore that. Huh? So for example, crash stop is a special case of omission. Okay? So an omission can remove sends and receives. Some of them are removed. But if we remove all of them after a certain event, then it's exactly like the node is crashed, right? So crash stop is a special case of omission. So if we can solve omission, we already solved crash stop, you see? So that's one thing. We can even say more. What about crash recovery? So omission is actually a special case of crash recovery. Okay? So how can we see that? Well, crash recovery, it means the node crashes and eventually it reboots and it uses a stable storage. It can reuse a stable storage. Now assume the node is only using stable storage and there's no volatile, it's only the stable storage. That means when it crashes, all the memory is still there when it reboots. In that case, it's identical to omission, right? So when it crashes and it reboots, everything in between is like it doesn't send, it doesn't receive. So it's just the same as an omission while it's crashed. So if there's no volatile, if there's only stable storage, a crash recovery is the same as omission. But crash recovery has more than that. It has stable storage, but it also has volatile storage that disappears when it crashes. So this is not the same as omission. Volatile is not the same. See? So assume that we have crash recovery, but the nodes are using some volatile memory. That means when the node recovers, it actually forgets things. Okay? So, but it's not the same as omission. Omission is just send and receive are forgotten. The state is not forgotten. So crash recovery is like an extension of omission. It does more than omission. It's like amnesia. Oh, it forgets something. Okay? The volatile storage disappears. But omission, that does not happen. Huh? So crash recovery will extend omission with amnesia, forgetting part of its state. But if we have no volatile memory, then crash recovery is the same as omission. Huh? See? So it's like extending omission. Omission is a special case of crash recovery, where everything after a certain event. So it emits everything, but emits everything after a certain event, and it comes back to normal after it recovers. Okay? So that's the hierarchy. And of course, crash recovery is a special case of Byzantine, but Byzantine allows everything. It can remember part of the state, forget part of the state, does everything. So there's actually a hierarchy here. So here the red oval is all the Byzantine possible faults. Crash recovery is this brown oval. So the dark green one is emission and the light green is crash. Okay? So if you solve Byzantine, you solve everything. If you solve crash recovery, you've also solved emission and crash. If you solve emission, you also solved crash. If you solve crash, then you only solve crash. You don't solve the others. So these are the four main kinds of fault modes that you have to assume when you build the distributed system. Usually, we're going to talk about crash stop. When we do disk algorithms with disk, we're going to usually talk about crash recovery. But sometimes emission and Byzantine are useful. Byzantine is useful in very malicious software that is going to be attacked very strongly. So sometimes that's useful. And emission, sometimes messages, if messages can get lost, it's good to talk about emission. Okay, so this is the kind of faults we're going to talk about. So that's for the failures, for the nodes. For the channels, we also have failures. So we have nodes talking in channels here. So we have here the nodes and the channels. So now we talked about, this is the failures for the nodes, but the channels also can fail. So we have to talk about that. So we're going to talk about different kinds of failures for channels. So the basic one is called a fair loss link. So when you send a message, it delivers the message. So the message arrives with non-zero probability. So the network is connected, there's no partitions. If you send it, some probability, 30%, 90%, maybe 99%, whatever. There's some probability that it will arrive. This is actually the basic assumption. Okay, this is the basic assumption for internet kind of communications. So fair loss is like the ground floor. And we're going to build on top of that. So we're going to build two levels on top of that. One of them is called stubborn links, and the other one is called perfect links. So a stubborn link will deliver a message infinitely number of times. This is a very kind of strange thing. We'll see why we do like this. So we send a message, it actually arrives an infinite number of times. That means we're sure it eventually gets there as many times as we want. That's why it's called stubborn, right? It just keeps delivering it. And the perfect links is that when you send a message, it's delivered exactly once. So why do we define like this? Well, because we're going to show you the code for these. So I'm going to show you the code for stubborn links, and perfect links. And when we build algorithms, usually we're going to use perfect links as the basis. We're going to use this one. And what does the internet provide us? What's like the ground level? It's usually going to be a fair loss link. So something like UDP, IP, is giving us like a fair loss link. Okay? Perfect link is more like a TCP. Okay? So this is like the foundation. Remember we have this layered structure. We have the channels and then the middleware, algorithms and application. So the bottom level is this, huh? And the bottom real foundation is going to be the fair loss links. Okay? So a fair loss link looks very simple. I have nodes here. Here's I call it FLP2P, fair loss point to point. So when PI sends a message here, a request, then this message is delivered here. So it's sending to PJ, message M. When the message is delivered, it gives you the source node. It's coming from PI, message M. And PJ can send a message back to PI. Okay, so they're point to point. and you have a send, a request, and indication of the message delivery. So that's what it looks like in terms of the messages. Okay? So there's an interface here. It's called fair loss point-to-point. Has two events. So there's a request. Remember what the request is? Request is going down, huh? Remember that? An indication is coming up, huh? So when I want to send, I do a request. Fair loss point-to-point, send, destination, message. And when a message arrives, it's an indication comes up. Fair loss point-to-point deliver, coming from the source node, message M. So these are the events, very simple. And it has three properties. So this is very general. We're always going to specify the algorithms in terms of properties. Okay? So there's three properties here. FL1, fair loss property. FL2, finite duplication. And FL3, no creation. So fair loss. If a message is sent infinitely often from PI to PJ, and neither of the node crashes, so they're not crashing, they're correct, then it's delivered infinitely often by PJ. That means a lot of messages can be lost. Huh? This is how we model the probable arrival. Huh? If you send it, maybe I send 1,000 times and 300 arrive. I send 10,000 times, a couple 2,000 arrive. I send 1,000,000 times, maybe only 150,000 will arrive. But when one of the numbers grows, when the send grows to infinity, the deliver will also grow to infinity. So messages are always going to be delivered. The more messages you send, whenever you send messages you send infinitely often, you will deliver it infinitely often. Okay? And then the second property is finite duplication. So, okay, when I send a message, maybe it arrives twice. That's possible in the internet. So this is actually kind of modeling what IP is doing. Huh? If I send a back packet, it can actually arrive twice. And the reason is, maybe it goes to one router, and the router forwards it to another router, but it doesn't know that it actually got there. It thinks that that second router has crashed because there's some problem, ingestion, whatever. So it says, oh, that router crashed, so he tries another router. But maybe the message did actually get through. So ultimately, the message might arrive twice. Okay? This can actually arrive on IP. This is a situation that can actually arrive. And there's really no way to avoid it at this level, at the simple router level. So we define it, and it's called finite duplication. If a message is sent a finite number of times from PI to PJ, then it's delivered a finite number of times. Okay? That means if I send it 100 times, it will only arrive, I don't know, maybe 200, or maybe 100, or maybe 50, but a finite number of times. The message will not be duplicated infinitely many times. If I send a message in the system, it will only arrive a finite number of times, and not an infinite number of times. Okay? So it will, the duplication will not be infinite. There's only finite duplication. And finally, no creation, no message delivered and never sent. So the network is not going to invent messages. All the messages are coming from the source nodes. Okay? So they're coming from the source nodes, they arrive with certain probability, but they're not duplicated infinitely often. Okay? So these three properties, very precisely, they define this, they define fair loss links. And now, you know the question I'm going to ask you, right? Do you know what I'm going to ask you now? You know, don't have any idea? I'm going to ask you a question. Whenever I see properties like this, then there's a question I'm going to ask you is, are they, no? Really don't have an idea? You must have an idea, right? You don't know. Are they safety or liveness? Okay. So these properties, actually I mentioned it, but this last week was maybe too complicated. So each property is going to be either safety or liveness. It's a really good exercise to figure it out. So remember how safety and liveness work. So safety is when the system is broken. Okay? You break the system, you drop the egg, it breaks. Liveness is whenever something good can always happen. The property can always be satisfied. And breaking it takes an infinite time. Okay? So the first one, is it safety or liveness? What do you think? We're talking about infinite things here, huh? So this one, sent infinitely often, then it delivers infinitely often. This is not possible to break it in finite time. Huh? We're talking about infinite things here. Huh? So it's not a safety property. Huh? It's a liveness property. Huh? When I'm sending the good things, if I keep sending messages, the good thing is that eventually it will arrive. Always. When I keep sending more, it will eventually arrive again and again and again. So this is a liveness property. Okay? Right? Agree with that? If I'm saying something wrong, you have to tell me, yeah? First of all, sometimes I make mistakes. It's extremely rare, but it happens. But also I can try to fool you. But in this case, it seems to be right. Huh? What about the second property, finite duplication? If it's sent a finite number of times, it's delivered a finite number of times. It cannot be duplicated infinitely many times. So how do you break this? You break it by duplicating infinitely many times. Huh? That's how you break it. But you can only break it after infinite time. Huh? So this is what? It's what? You tell me. Ooh, it's tough. No? Yes? It's a liveness property, huh? It's a liveness property. You cannot break it in a finite time, but you can break it in infinite time. So the good thing is that eventually you will no longer deliver the message, huh? What about the third one? So here we have two liveness properties. Remember we said that usually you need both in a real system, huh? It's very easy to satisfy one or the other. The real problem is when you have these two that are trying to go against each other. Like, remember the green lights? So, liveness means the lights are green. So just make them all green all the time. But safety means that the cars don't crash. No? Safety means that there's no two that are green that are going to crash. So the easy way is to one or the other. The problem is when you have to have both. So this third one, what is it? Safety or liveness? Yeah? Somebody from over there? No? What happens if the network creates a message and delivers it? What has happened? I've broken it. Huh? It's broken. And anything I do after that cannot fix it. It's broken. So what is it?
Safety.
It's a safety because I can break it in finite time. Huh? I can break this. So this is a safety property. Yeah? So we have two liveness and a safety property. So this is the fundamental thing we're going to start with. These fair loss links. You see, it's kind of subtle. Huh? These properties, they're very precise, but it's not always intuitively, completely obvious what is the right way. You see, they're kind of subtle properties. Huh? But it's important to think of very precise properties. And then you figure out whether they're the right ones or not. Huh? So fair loss is like this. So fair loss, I'm not going to give implementation for fair loss, because we assume that the network gives it to us. This is like the assumption from the start. We assume we have some protocol that gives it, okay, fair loss, with these three properties. An internet protocol, IP, does satisfy these three properties, okay? So this gives you a nice specification of the starting point. All the algorithms in this course, or at least the first half, are going to be built on top of fair loss. So we're going to build a huge number of things on top of this simple foundation, okay? So the first step is called these stubborn links. These are funny ones. So it looks almost the same, the interface. SP2P, so stubborn point-to-point. I send a message to a destination, and this is the request. So it goes down into the system, the indication comes up, it delivers the message M sent by node source. And we define it again with properties, very precise properties. Here we have two properties, these stubborn links. So the properties are SL1, SL2. So stubborn delivery, if a node sends a message to a correct node, PJ, and PI does not crash, so both are correct, then PJ delivers M an infinite number of times. That's the stubborn delivery. So you send a message, it keeps arriving. And then there's the node creation. If a message was delivered by a node, then it was sent by a node. So there's no message created in there. You see, there's no finite duplication thing here, because here we're actually assuming it's going to arrive an infinite number of times. Huh? So what about safety and liveness? So the first one is what? You tell me. This time it's easy, right? As long as there's life, there's hope. That means I've sent a message and I have a prefix of an execution. I can always find an extension that delivers the message again, right? Always, because the number of deliveries is infinite. So that makes this what?
Liveness.
Liveness, huh? This is liveness. And this one? This is the same as the previous node creation, huh? So no creation, it's safety. So this one can be broken very easily, yeah? But if we don't break it, then no messages are created, then it's safer. That's safety. So we have a safety and a liveness problem. So that's a stubborn link. And we're going to show you some code now. So basically, the idea is very simple. We're going to build the stubborn link on top of fair loss. So we're going to use the fair loss underneath. So we're going to have something like this. We have fair loss point to point, and the stubborn point to point is going to be on top. So the indications and the responses are going to be like this, and on the other node it will be like this. So the system will look like this. So the fair loss point to point, we assume it exists, and we're going to build the new code, the new things on top. Okay? So it's very easy, huh? The sender will store every message it sends in a local variable called send, and periodically, so it has a timer, and periodically it does more requests to FL. Okay? So it periodically resends. So this is the idea for the algorithm. And we can prove these two properties. So now we have, so for fair loss we have three properties. FL1, FL2, FL3. For stubborn links we have two properties. We can actually prove the SL properties assuming the FL with the code of this algorithm. So that's how we're going to reason. We're going to build a system like layers, and each time we're going to prove the new stuff using the old stuff. So we can prove these two. So if a node doesn't crash, sends every message infinitely many times, and because of FL1, they will be delivered infinitely times. The lossy link can only drop a fraction of them. Sending infinitely often will still deliver infinitely often. So there's going to be an infinite number of sends going down, because I store the message here. So I send one message here, this is going to do infinite number, and there's going to be an infinite number coming here because of FL1. Okay? And the no creation is the same as the no creation of the fair loss. So we can prove the correctness. We can also look at stubborn links in the formal model. Remember, we have an execution, configurations with events. So the stubbornness, we can actually add it to the formal model if we want. So if a message appears in the outbuff, then the idea is that the delivery will happen infinitely often without removing the message from the outbuff. Okay? So this is another way of looking at the stubborn delivery. Yeah? So I'm going to show you the code for this. So this is the typical kind of code we're going to write. We're going to have these little blocks of code where we have an upon event. So this is the receive, and then we're going to do some actions. Okay? So remember we have the init event. So the init event, there's a local variable called sent, which is a set of messages. It starts out being empty set. And then we have a timer. So we assume we have this timer. We start the timer with a time delay. And then after every time, there's going to be an event called timeout. And this event, when we get it, we will do this code here. So for all messages, destination message pairs in sent, we will do a fair loss point-to-point send, this for loop. And then we will start the timer again. Okay? So that's very straightforward. And then there's other piece of code. So this is the messages coming down and up. If I do a stubborn point-to-point send, all I do is I add the message and its node, destination node, to the send set. Okay, so this request coming from the top here is just going to update the sent variable. And then the message in the other direction. So if there's a fair loss point-to-point deliver coming up from the bottom, it's just going to cause a stubborn point-to-point deliver. So the message coming into the stubborn box is going to be a response going out of it. Remember, the trigger is a send. So this is the code for this is our first kind of algorithm. Okay? So all the algorithms are going to be sort of defined like this. We're going to have properties like this, formal properties, and we're going to write some code. And the code is going to look like this. It's going to be these boxes. These are the yellow boxes. These are yellow boxes where I receive something and then I do something. So upon event is receive and trigger is a send. Okay, is it clear, this code? Yes?
Sorry, at what point is there something in the send set? Because it starts
empty.
And then at what point does it...
It's here. Whenever I do a stubborn point-to-point send, it will add this to the send. So it's 2 pages, the code. So it's these 4 little boxes. There's 2 here, and then there's these 2. So this one, all it does is put something inside send, and then there's the timer will look at this and send messages down. It's okay? It's clear? So this is the style that we're going to use. We're going to have these local variables, which are like very general things. Here there are sets of pairs. A set is a set of these pairs. We're just going to use whatever. It's like a pseudocode. But if you want to write the algorithm, you can convert this to whatever language you want. And later on in the course, when we do the project, we're going to use Erlang. Erlang actually is in some sense very similar to this. Has a very different syntax, but the idea is very similar. Messages receiving and you sending, and you have local variables. Okay, so this is how these stubborn links, they work. Right? It's okay? It's pretty clear? It's not very complicated, right? It's a simple code, huh? It's easy to understand how it works, huh? So most of the algorithms will be sort of easy, but we're going to build on top. So eventually, the algorithms will be very sophisticated. But this is, stubborn one is very straightforward, huh? So now, from the stubborn link, let's go to the perfect link. So the perfect link is going to be on top of the stubborn one. So we will have another layer here. This one is called the perfect point-to-point send, PP2P. Again, the interface is almost the same. Huh? For perfect point-to-point send, message to destination, deliver message from a source. And also it has properties, PL1, PL2, PL3. Perfect point-to-point. And then we're going to show how to write it. Like this. So we have these three properties. So here we have the properties. So PL1, reliable delivery. So if neither PI nor PJ crashes, so they're both correct, every message sent by PA to PJ is eventually delivered by PJ. That means you send a message, it arrives. And then the second property, no duplication, it's delivered at most once, not more. And no creation, it's delivered unless it was sent. So here it's delivered, that means at least once, PL1, PL2 at most once, so together it means the message arrives exactly once. Yes?
For PL1, isn't it eventually delivered to PJ, not by PJ?
Yeah, I mean, it's what they say, it's by PJ to the application. So yeah, it's a way of speaking. So usually when you say deliver, it's delivered to the application and by PJ. So it's by the perfect point-to-point box to the, so it's basically a message going out of this box. You can say to here. If you say by, then you're assuming it's from P perfect point-to-point going up to the application. If you're talking about the application itself, then you can say to here. So it depends on your point of view, whether you're looking at this box or you're looking at the application which is on top of. So if you're looking at the application, then you can put to here. It's a way of speaking. So deliver means it's goes to the destination that you want it to go to. So delivery can be to, it's not just to a node, it's to also to a box on the node. So I'm going to ask the same question again. First one is what? Safety or liveness? You'll get used to this. Pretty soon it'll be very easy. Safety or liveness for the first one?
Safety?
I hear both. So how do I break this? By never delivering, but I have to wait infinitely long for that. If I have a prefix and it's not delivered in that prefix, then maybe I can do an extension where it's delivered, right? It can always be delivered in the future, but if it's already delivered, then it's okay, then I'm done. So what is it? Should be pretty clear, right? Liveness, huh? It's a liveness property. So it's whatever, something good will eventually happen. There's no way to break it in finite time, huh? But if I'm in a certain prefix and it hasn't happened yet, it can always happen in the future. So as long as there's life, there's hope, huh? So you can always extend the prefix to make it happen, is what this says. Huh? So this is liveness. Huh? What about this one? Every message is delivered at most once. Come on, you guys. Somebody else has to say. Somebody in the back. No? Oh, you guys in the back there. No? No ideas? Come on, that should be easy, right? It's delivered at most once. So how do you break this? You can break this, huh? How do you break it?
Deliver more than once.
Deliver more than once. So what does it mean if you can break it?
That's safety.
It's a safety property, yeah? Yeah?
Yes, but you have to wait infinitely long in order to be sure that it's not sent another time, no?
No, once you know that it's twice, you don't care what happens in the future. It's broken right now. You don't have to wait. Yeah, so this every message is delivered at most once. It can only be satisfied by waiting infinitely long. That's safety. That's a safety idea. Huh? You're never really safe. Some dangerous thing might always happen. The only way to be truly safe is to wait infinitely long. But you can actually break it in finite time. Huh? This thing, huh? So this is safety. Notice that I don't have a property exactly 1. It's actually really nice. See, there's no, I mean, yeah, you can combine properties, huh? You can make a property exactly 1, which is like a combination of safety and liveness. But it's actually nice to separate the safety and the liveness, to separate properties. So in this course, all of the specifications are going to be like that. They're going to be specific safety and liveness. And that makes it actually very nice, and it makes the reasoning easier, and it makes it easier to really to think about the algorithm. When you start combining the properties into complicated properties, and you're mixing safety and liveness, it makes life more complicated. So it's actually nice to separate them out. Huh? So when you write your own algorithms, now or later, it's nice to have them separate safety and liveness. Huh? And of course, the final one is what?
Safety.
Safety, huh? We saw it already many times. Huh? Okay? So the perfect link. So we have these three, we have already now 3 boxes. We already are building a layered system. Huh? Yeah, okay, so we already, So we can of course implement the perfect link. And here it's kind of opposite to the stubborn. So instead of having like a set, in the receiver we have a log. So a set of all the messages that have been received here. So if the message is received twice, we can make sure it's only delivered once. So if the message comes up here, the same message comes up more than once, we put it in the log, and we only make it go up to the application once. Okay? So it only gets delivered to the application once by using a log. Okay? And then we can prove the correctness. So these 3 properties, PL1, PL2, PL3, because of the properties that are underneath. So we're going to build this on top of stubborn links. So reliable delivery. So remember, it's actually delivered at least once. So this is guaranteed by the stubborn link because I know we're going to get it an infinite number of times. But because of the log, only one of them is propagated upward. Huh? So no duplication. That's the log guarantees that. No creation. So this is guaranteed by the stubborn link. Okay? So this one has no creation. And of course the no creation comes from the fair loss underneath. Huh? But the stubborn link also guarantees. So you could prove this, again, you prove these properties by looking at the properties of the thing underneath. See, we're building like layers, huh? A layered system. So we can write the code for this. So perfect links uses stubborn links. So here we have delivered. So this is the log. It's a set of delivered messages. It starts out to be empty. When I send a message, I do a stubborn send, so it just goes down. When there's a request, I just go downwards to the stubborn. And when the stubborn one delivers, I check to see whether it's already delivered. And if it's not, I put it in the delivered set, and I trigger a message going up. So this avoids the duplication. I think that's all. There's no other code. So this code is very simple. So this is pretty clear, right? This code. It's kind of nice, right? It's very simple. So, yeah. So, perfect links. In the rest of the course, we're usually going to use these perfect links. We're going to assume perfect links. Sometimes they're also called reliable links in most of the course. Messages exchanged between correct nodes are delivered exactly once. Okay? Usually the messages are going to be unique. Each message will have like a unique ID. If we send the same stuff more than once, it's usually going to be two separate messages. So each message, that's the usual thing, unless we say it differently, yeah? So why do we need stubborn links? Actually, there's a couple of reasons for stubborn links. One actually is that it makes the code very simple. So you might think stubborn link, what is this useless, weird thing? Delivers an infinite number of times. Okay? This thing. But in crash recovery, this can be useful because when the node comes back, it can recover the messages that were lost before. But also, it's important for design. So the code is very simple here. See, this code is very simple, this code is very simple. So separating the levels like this makes things very simple. See that? So even though probably a real implementation is not going to do exactly like that. So there's a difference between the correct implementation and optimized implementation. So the important thing is to start with the correct one, correctness first, and then optimization later. So with this implementation, with this design here, the correctness is very easy to see. We've defined it formally, we can prove it. So this is correct. Now we can always optimize. And if you look at something like TCP, okay, TCP is a kind of perfect, it's a reliable byte stream, so it's a perfect link. Yeah? So TCP actually optimizes this. So you know how TCP works, right? You've seen TCP, most of you? Who has seen TCP among you guys? Most everybody. Good. So TCP is using this window approach. So basically it's optimizing this. So it has sequence numbers and it has the window, so it knows when a certain packet has not been received, and so it can request. So it's basically an optimization of these stubborn links, okay? Because in real life, as soon as you get an acknowledgement back that you've received it, the stubborn link can stop sending, which is what the TCP acknowledgement is doing, okay? So, but this is a very simple design. So in this course, we're going to show you really simple designs. And the reason for that is we're going to have very sophisticated algorithms. So if I show you the real optimized design first, your heads are going to explode. You won't be able to understand, okay? So the only really way to do it is to start with a really simple design first. And you'll see it and you'll understand that it's correct, even for very sophisticated algorithms like the consensus algorithms we're going to see, and some of the broadcast algorithms. They're very complicated, actually. So that's why the simplicity of the design is super important. And you can always optimize it. So you know the famous statement by Donald Knuth, that premature optimization is the root of all evil. So don't optimize so quickly. So in this course, I want you really to understand these algorithms. Huh? So that's all for TCP. Let's make a break now. So this actually gives you already an idea of how we're going to organize the course. Huh? Properties, layered structure, simple algorithms, optimization later, and correctness first. Okay? So we make a break now.